everyone. So I'm just going to go through the folks as they are listed on my Zoom. So Daeil, do you want to kick us off?
Yeah, sure. Just a quick intro to myself. My name is Daeil Kim. I'm one of the founders of AI.Reverie. We are a computer vision startup that specializes in creating synthetic data. And our goal is to be able to create a lot of really good synthetic data with our procedural world generation platform. So to sort of make training computer vision a lot more easier and robust.
Awesome. And then Abhishek?
Hi, I'm Abhishek. I do computer vision research and development at Apple. So largely my role involves creating all the computer vision smarts that go into the iPhone camera and photography experience.
That sounds really interesting. Can't wait to hear more about that later. And then Vladimir?
So I work in Lyft in its self-driving division. So Lyft has both ride sharing and of course like self-driving. It's pretty like popular topic these days. So I work on computer vision and other deep learning applications to the problems of perception and mapping in the self-driving.
All right, and then last but not least, Alyssa?
Hi, my name's Alyssa, and I work for Appen. And what Appen does, actually we are, many of you on the panel and probably in the attendees are customers of ours. We do human data annotation at very large scale for big companies as well as lots of startups who are building out machine learning based products and services. So everything from home assistants that you may use to large search or social media companies and lots of self-driving or computer vision applications as well.
That sounds great. Yeah, I don't think I've specifically used your products before, but that's definitely something that I know lots of my peers have needed to use. So, and then for everybody, my name is Jessie Shanahan. I'm a lead data scientist at Booz Allen. While my background's in astrophysics, my focus at Booz Allen has been the humanitarian applications for AI, and computer vision plays a huge part in that. And so that's really been my focus so far. And while I think AI and machine learning have a lot of wide-reaching implications for humanitarian aid and disaster response, computer vision in particular seems to be kind of at the forefront. So excited to be here today to talk more about computer vision. And I think we're ready for our first question. So to kick us off, is computer vision commonplace within enterprises that have machine learning models in production, or is it still early days? And so if anyone wants to take this off, let's hear all about your experiences with enterprise level computer vision.
So we work with a range of enterprises. I'll just start things off, and I would say yes and no, depending on where that company is in the sophistication of their journey into machine learning. So some companies that we work with are incredibly sophisticated and have very, 10-year plus long running computer vision models that do things like content moderation, or even like back office, receipt transcription or check processing, which are computer vision applications. Others are just getting started with their computer vision journeys and are much newer to this. So a huge range. Some companies, completely rely on computer vision for their entire business, and others don't.
I think that's largely been my experience as well. Is it really depends on the company, on the organization. Some have deployed machine learning, but it's very, very simple and very easy and explainable. But I found that computer vision can kind of stray into that black box territory sometimes. And so that lack of explainability can be difficult in adopting it kind of enterprise-wide. Has anybody else had similar experience, different experience?
Yeah, that's largely true. What you guys said. I still feel that there is computer vision is often looked at as a slightly niche field, within the broader ML and AI community. So I still see a lot of potential. I still feel that it's still early days for a lot of companies to adopt a lot of the technologies that come out of the computer vision field. And it's not just true for small companies. A lot of big players in the field that have established ML groups may not have fully realize the potential that could come out of using some computer vision techniques for their problems.
Why do you think they haven't realized that yet?
It's probably because they've so far been I guess busy trying to hit the bigger balls out of the park. focusing more on the traditional ML problems that can add more value to their business. But as those things saturate, the value adds can come from these other modalities, understanding images and videos better and see how that can improve, their business model. So it's probably not has been as important for them yet. It could also be just because of lack of, domain expertise in that area among people who are already there. So it's a bit of both that I see in a lot of companies today.
So maybe I'll give a slightly different answer with two examples. So, one example of a company or organization that's been using computer vision for a really long time is the US Postal Service, right? They've been using OCR, optical character recognition, I think since about the 60s. They were probably one of the first companies to really put it to broad scale business critical use. And, that's been going on for a long time. And, they have very sophisticated, handwriting recognition models. On the other end of the spectrum today or yesterday, or this morning, IBM actually announced they're getting out of the facial recognition business because they are, underwhelmed with how the technology is being applied by some of the customers who are putting it into practical use. And I would say those two examples are sort of good explanations of the range of what's going on in computer vision, right? So some companies have invested heavily and are continuing to invest and use this for mission critical processing. Other companies are saying, we did some experimentation in this field. It didn't go so well. We're worried about bias that we're introducing. We're worried about unintended consequences. We're worried about sort of negative applications of misusing computer vision technology. And so we're actually going to pull back from it, right? And so I think there's an incredible range, just like there are with lots of different technologies. I don't think it's unique to computer vision. It's more speaks to the sophistication or the journey or the application that the company is on.
That makes a lot of sense. Daeil, were you going to say something?
Oh yeah, I was just going to add and confirm a little bit of what I'm hearing here as well. I mean, in terms of our particular experiences, we primarily work with like Fortune 100 companies. And so what we're finding is that if it's not necessarily critical to the company's mission, then it's often sort of not nearly as invested. It's still early. I think it's really just early days. I think it's still pretty new. There's still a lot, unless you're like, a company that needs to really get this done right. I'll give an example. One company we're working with, Blue River, on helping them sort of detect weeds in crops. For them, computer vision is critical. If you don't have a system that can actually detect that and segment that out with an algorithm, then you really don't have the technology that can be usable there. So that's where we really found a lot of excitement around. But having said that, even though it's small, we think it's going to grow quite large, given once these tools are built and the technologies get easier to use.
Definitely, and I would agree there. I think, to kind of piggyback off what Alyssa was saying about IBM withdrawing from computer vision, I do think that if we want this industry to grow and we want this in particular to become larger, more widespread and used, then having that kind of ethical framework or a way to address the concerns of a lot of these consumers is going to be kind of critical, because these are concerns that are being raised, and rightly so, and they're growing. And so I think that's going to have to be, I think, an area of future importance and hopefully current importance if we're going to see the industry expand. All right, well, I think we're probably ready for our next question. So what is unique about a computer vision project versus other machine learning projects within an enterprise setting? And so Vladimir, I'm going to pitch this one to you because you haven't spoken much and I want to give you a chance.
There are like some similarities in both of them, but what I've seen in companies that I worked in, including Lyft right now, you need slightly different talent, slightly different expertise. For many machine learning, traditional machine learning models, you need some data scientists, research scientists, and people that do some stuff in maybe not great software developers. When you talk about deep learning, computer vision, and some other stuff, you need people that are more skilled in writing production quality code and being scalable systems. So even if you're looking for talent that you're hiring, you're looking for slightly different people. Another thing, computer vision is very data intensive. So I mean, if you're talking about retail, about maybe some other things, time series, your data sets, they're big, but not that huge. When you're talking about high definition computer vision problems and you're working with large data sets, you get something like terabytes, like tens or hundreds of terabytes of data, and you need to process this efficiently. You need to build some kind of like whole ecosystem. So in this set, you don't care about researchers and like latest state of the art anymore. You care about ML ops and this corresponding disciplines. Yeah. So basically they're similar, but really different. And yeah, there's overlap in terms of mathematics and maybe in terms of like training for both of these like divisions. But I would say these days they're trying to diverge.
Okay. And what about anyone else? Has anyone had a different experience, or do you find that Vladimir's explanation is kind of what you found as well?
Just to add to what Vladimir said about data, I also feel that probably in the enterprise setting, the issue of adapting to a specific domain becomes important. So it might not always be possible to just reuse existing data sets that have been collected for some other purpose to solve your specific niche problem in the enterprise, right? So that's where investment in data is required, and that's why people like, I guess, Daeil and Alyssa come into the picture. You really have to collect data for your specific use case, which may not be general purpose. So that might become a challenge for doing a lot of these things in the enterprise.
I think one of the things that just sort of building on the importance of data in computer vision is different from other data types in machine learning. Everyone, as humans, we trust our eyes, right? And we trust what we see as truth. And we rely upon that visual input very heavily when navigating the world for many people. And that is, I think, different from other forms of machine learning, because most people, this is not true for everyone, but many people rely less heavily on what they hear or what they read, right? And so visual processing, everyone thinks they're a computer vision expert, right? Because everyone thinks they can trust what they see. And those are generalizations, but I think unfortunately in computer vision you can't always trust what you see, right? And you can manipulate the data, and as has been shown over and over again, right? Many of us, right, have virtual backgrounds right now, and it's not quite so true that I am sitting on a backdrop of the Golden Gate Bridge behind me, right? That's a fallacy. And so I think more so than perhaps in other data formats, there's nuances with reliability and trust and accuracy in computer vision that can be really hard to specify or articulate or document versus with other formats. Not everyone thinks they're such an expert in natural language processing, right? Because I may not be a linguist, or I may not, specialize in the English language, or I may have a little bit more insecurities around my ability to process language, where I think humans have less insecurities around their ability to process visual information. And so it can be a higher bar or bigger challenge as computer vision experts or professionals to get widespread business sort of input and agreement around what the goals are, or the sort of accuracy or objectives are for a particular computer vision initiative or project.
I'd like to add also, I think that's worth it, that's interesting, is you brought up NLP, Alyssa, and I think there's something interesting there with computer vision, because oftentimes cameras are not all created equally, right? And to Abhishek's point about how you have to very target the domain in which you're trying to actually train an algorithm with, that might just be affected by the camera sensor itself. And so the kind of ability to sort of easily take one data set, and I wish Microsoft Coco data set can solve all the vision problems in the world, but unfortunately it can't, because cameras come in all sizes and sensor types and all that stuff. So that does actually add an interesting complexity, especially to our work. I'm sure with Appen as well, there's a lot of stuff where you get images where it's like, whoa, I can't even, I have no idea where this is coming from in terms of.
Well, it's also like the language that we use to describe what we see with our eyes is different, right? So I'll take, the concept I use a lot to references is the concept of the color green. In the United States, there is a visual representation of the color green that is different from in Japan, how that same language is used to describe a visual outcome, right? So that's just one example of how humans can have different takeaways of looking at the same stimuli, right? And in machine vision, it's your job to codify and document all this kind of stuff and create decisions off of visual input. And even two humans standing next to each other, looking at the same piece of information, are going to have different conclusions from the same visual input based on your worldview and your context.
Really interesting point. And I think, while it's still, I would say, a very new application in astronomy, the use of computer vision has kind of had mixed results. And so specifically what I'm thinking about is there are a lot of data sets out there, more data than astronomers could possibly sit through and reasonably classify. And so there's been a lot of attempts to say, identify objects, classify them, and the results have always been mixed. And sometimes, people point to problems with a particular approach, the algorithm, whatever. But actually, Alyssa, to your point, I found that sometimes it's about people disagreeing about what's actually in the image. And so maybe there's this fuzzy blob, which most things in space are fuzzy blobs, and one person sees it a certain way and another person will see it another way. And so those disagreements become particularly apparent when you try to codify things and have an accurate machine classification, because regardless of what the machine classifies it as, you're going to have disagreement amongst the human experts. So it's a really interesting point.
I would like to do this. I had a few projects related to medical imaging, and often, like, how do you label this? Let's say I cannot label because I look at medical imaging and I have no clue, I don't have domain knowledge. And people that provide the data, they ask like doctors to do the labeling, and then you just look at this labeling and train something of this. I don't remember any single instance when doctors agreed. Basically, so, and another task that you need to deal with, you have some labels, some semantic segmentation labels, like cancer cells or something like this, and you have like for the same image, you have 6 different like labels, and you look at this and you need to figure out how to deal with this disagreement between domain experts.
So Vladimir and Jesse, just to follow up on that, what do you guys think should be expected out of a computer vision algorithm in such situations where it is very difficult for even humans to agree on what the right label or the right prediction should be? What do you guys think should be the expectation out of any?
In this sense, network matches my expectations. In the regions where doctors agree the most, the probability, the confidence of my network predictions should be the biggest. In the regions where they disagree the most, the variance of the predictions, this uncertainty should be the largest. In this sense, that's what I would expect. And again, I believe that if you get this disagreement and you train some network and show some uncertainty, probably if you give the same predictions to the same doctors who label this image, they may change their opinion or maybe converge to something that's more reliable.
So one of the approaches that I've seen with dealing with this was very interesting, and that's the approach used by Zooniverse. And so this is kind of a public citizen science project where anybody can create an account, learn how to classify images or sounds, and then provide labels. And so you're going to have, because these aren't domain experts, but hopefully for most of the projects, it's very straightforward classifications. Is this, a galaxy with arms? Is this a perfectly spherical object? Things like that. But still you have, to Vladimir's point, you still have a lot of disagreement. And so the bonus of having people create those accounts is that you can kind of track how they classify compared to the majority over time. And you can provide some kind of statistical down-weighting and up-weighting of people who are either less or more accurate, respectively. And so that way you're getting kind of a consensus of a sort. It's a majority consensus. But even then, the data that came out of there, we would apply certain cutoffs. So if we wanted an object to have a particular classification, we might say we want 60 or 70% of the majority to agree on this or above. And the kind of objects that were more contentious, we would disregard. And I think that's just the luxury of having hundreds of thousands of images. But that's one of the approaches that I've seen that's been effective.
And maybe just to be a little controversial there, I actually think there's a bunch of challenges with that approach, right, of sort of majority rules, right, or disregarding data, because you can end up not having completeness in your data set, right? So take facial recognition, for example. If you can't agree around what race someone is, right? And let's say, someone labels me as white, someone else labels me as Russian, someone else labels me as, I don't know, non-Hispanic, right? Those are all sort of different categories or labels. And truth is sort of a moving target, right? And that's not necessarily something that can be seen visually. And so if you're training a computer vision algorithm to identify race and you don't have good agreement and you just disregard sort of labels in a particular category, then you're not going to sort of get to the objective or the goal. And so I actually think this is similar to any machine learning project and not unique to computer vision, but perhaps more important in computer vision is to very specifically, narrowly document and define your goals and objectives for the model that you're building, right? So a use case that's perhaps a little sensitive, but I was working with Adobe, right? They do stock imagery. And they have lots of different ways in which they categorize their images around different filters, different sort of aesthetic groups, right? And these aesthetic sort of artistic applications are nuanced and they're not widely agreed upon, but Adobe has a particular perspective around what it means to be a classical image and what it means to be, a different sort of descriptive, artistic type of image. And they apply these labels, right, with a particular objective in mind to define these categories and these classes. So I think that's really critical with computer vision projects, but any type of machine learning projects is ahead of time specify what you're going for and how that model is going to be used and applied, and then work backwards to do the data annotation. But to sort of go with like just majority rules, because we don't know what's in the data, you can sort of leave out or have unintended pretty negative consequences by allowing for too much ambiguity or disregarding data.
That's a really good point. And I think, on the one hand, if somebody misclassifies a galaxy, it's not the end of the world, right? But whenever algorithms or whenever machine learning approaches are applied to human data, there definitely has to be, I think, an increase in those concerns around proper use, around verification of the data, bias, ethical concerns about use. And so I would definitely agree with your point. But to move on to the next question, what are some top examples of computer vision models that you've built in your companies? Who'd like to start?
I don't think for us, we actually take a different approach of just building the model that the company is actually using, because for us, our whole thing is around benchmarking synthetic data and making sure that works on par and solves the problems that they need. And so we end up actually experiencing all sorts of computer vision models, everything from your basic faster RCNN or fancier architectures that maybe more be attention-based systems and things like that. So there's a lot of really cool stuff out there. The field is progressing quite rapidly. And so, there's always a trade-off on computation and speed and things like that. But for the most part, it's pretty diverse. I'm not sure that's a really great answer. I know you look at the top ML models, but one thing that we're really interested in is attention-based models. Facebook just came out with the DETR model that tries to sort of incorporate transformer architecture into the neural net to be able to ascertain things like where attention should be focused on in terms of the algorithm itself. So I think there's a lot of promise there.
Yeah, I've definitely heard a lot about that kind of being the next forefront. So what about anyone else? And if you don't want to talk about specific models, maybe use cases that you found interesting or applications for computer vision that you've been involved with that have been particularly compelling?
I cannot talk about stuff that I do at work, but let me mention this. So in Lyft last year, we hosted machine learning competition on 3D object detection, because if you know, in self-driving, companies like Tesla and AI, they rely on cameras, and everyone else is relying on combination of camera and LiDAR. And at this point, the question becomes, okay, you have like two modalities, both as like visual data, which is like dense but 2D, and you have like sparse 3D data from the LiDAR, and everything is changing with time. And how will you deal with this? And when you have these two modalities that are kind of different, and both of them are important and complement each other, you need to develop neural network that will be able to handle all of this mass of information in a nice way and solve tasks. So last year in fall, we hosted machine learning competition at the Kaggle platform. And there provided some baseline, and participants showed us pretty interesting approaches in terms of how to combine like 2D and 3D, and yeah, it was really interesting. So in many ways, like to extend this thought, in self-driving, we don't work just with images. We don't work just with LiDAR. We have a whole combination of different sensors. And this, in many ways, I believe is the next step in the computer vision, one of the probable next steps. So for self-driving combination of different data sources, again, when I look at research papers, I see people are trying to combine natural language processing and computer vision and this type of stuff. Not sure that like most of this research works on a production ready, but maybe in a couple years, they will open some really new exciting application that right now we don't even think about.
That's interesting, and that kind of combination of maybe either other wavelengths or other data sources. I've seen that a lot in humanitarian applications for computer vision, particularly the combination of satellite imagery and LiDAR. One of the uses that can often be used for is to automatically detect through change detection damage that's been done to an area following a natural disaster. You can also look at changes in topology following an earthquake or a mudslide to detect kind of destabilization in various buildings. And so it's definitely, I think, a very powerful combination of data. And I think that wherever possible, having many different data sources provides kind of a more robust foundation for whatever it is that you're building. So I definitely agree, and I think that's going to be an interesting area to watch in the future.
We've just because there's a couple questions that came in the chat around use cases in computer vision and retail industry. Maybe I'll speak to a couple of those. One question around inventory management and stock tracking. Seen a lot of examples of that. One of the things that I think can be really successful is around categorizing, clothing in a retail setting. So if you're Gap or H&M or, Urban Outfitters, you want to be able to allow your customers to filter by particular, clothing types. So if they click blazer, you want to make sure that all of your inventory comes up as blazer. And the difference between sort of a blazer and a trench coat, here, when I say those words out loud, you may have sort of a specific idea in mind of like, okay, well, a blazer is this, it has a collar, and it's, typically dark colored, and, you have a bunch of attributes. But in reality, for a store like, say, Urban Outfitters, there's a range, and you can sort of line up a lot of clothes, and there's perhaps ambiguity or differences around, where the line is exactly between what's a blazer and what's a trench coat. A successful computer vision application, I think, is around demarcating and delineating, kind of the differences between that to be able to tag clothing with a lot of different attributes, so that if you're searching for clothing, there may be differences between you and I and how we sort of define those definitions. Another example is around visual similarity search, which eBay has put to use really successfully, has been very public around, being able to take a picture of something and look for objects that are very similar in eBay's vast catalog of images that people are uploading. Another great use case in retail is around logo detection. So understanding if a brand has a particular mark or logo recognized on it, and you can either remove it from your website in the context of like a Society6 or an Etsy type use case, because that would be plagiarism to use a logo in an art format, and you don't want to be selling that. Lots of different use cases I could go on and on.
I've seen a lot of similar use cases actually. If folks have heard of like the iNaturalist app, it's this great app for the public to take pictures of birds, lizards, bugs, plants in their local area or wherever they are and classify them. But when you take a picture and you upload it, it automatically searches for the closest similarity and does it with such accuracy that it can propose a genus and a species classification for it. And those are then verified by human experts, but it's kind of a similar use case where you're able to kind of make those comparisons. Another thing to your label point that I've seen is in identifying fraud and identifying forgeries or like knockoff items. And so if there are, you know, a very telltale logo or style or structure, sometimes computer vision and classification can be used for identifying items that are fraudulently made. And so that's another kind of use case in the retail industry that I've seen.
One of the things we're working on is the cashless shopping, we actually built, we're working with 7-Eleven on this, and we're actually built a sort of simulated, you know, store game of sorts where people can go in and actually pick up 3D models of things. And there's a lot of really interesting computer vision challenges there around pose and grasp intention and things like that. But, you know, a lot of retail is also going into this sort of cashless shopping experience. And I think that's an area to look out for as well, too.
Definitely, and I think especially given the current healthcare crisis around the world, probably is driving a lot of the desire to have kind of the ability to shop from your home. Yeah. So, all right, well, let's move on to the next question. All right, so let's talk about training, transfer learning, data tagging, augmentation, enrichment, GANs, etc. What are the main considerations when training a computer vision model? And we've also had some questions in chat from people asking about approaches to get more accurate data or approaches dealing with data that perhaps you suspect your labels might not be accurate. So I think that also can come into training. So let's open the conversation up. Who wants to talk about training?
Maybe I can start. This is the business that we're in all day long. So there's a number of approaches around training. I think the easiest thing that anyone who's involved in a computer vision project is capable of doing is to help the team, if it's not already clear, to document and articulate and codify sort of exactly what business decision or thing that you're trying to get the computer vision model to decide, right? And what criteria is going to allow for that decision-making criteria, and where is the boundary between when something should be classed as, you know, one class versus a different class. So once you've documented that really, really, really clearly and in a ton of detail, and I'll just give one example because I think that one of the challenges here is everyone thinks that they agree and they think that it's easy, but when you get into the detail of labeling, it's actually really hard, and there's a lot of disagreement and nuance. And so something as simple as putting a box around a person in an image, right? That seems pretty straightforward. There's sort of 3 key words that I use, which is box, around, and person. However, what do you mean by a person, right? You know, what if someone is half in the frame or not? What if it's a child versus an adult? What if it's a cartoon character person versus, you know, a real person? What if it's, you know, a simulated person versus not? There's all sorts of nuances around just the word person. And so really sort of documenting that, that's, I think, the biggest thing that people can do for quality that's easy and something anyone can do. There's a lot to be done around scaling labeling and quality and doing that. You know, it's one thing for me to sit in a room and you know, once I've agreed on all this criteria and the instructions for labeling data, and then for me personally to like label 100 images or 1,000 images, it's really different to do 100,000 or 1 million or 100 million or 1 billion images at scale, and to have 100,000 people follow instructions in the exact same and apply those instructions consistently. And so there's a lot of tooling and technology that can help scale out those processes. And so, you know, it starts though with documenting exactly what the instructions are. So some, you know, tooling around that scale, around sort of gold standard labels, hidden test questions, being able to do fraud detection, being able to have bonuses or incentives around high quality work, being able to route data to multiple humans to have verification and agreement around judgment, or this concept of dynamic judgment. So if there's a lot of disagreement around one particular label or image, to route it to, up to 10 or up to 100 people to get more and more opinions about that particular image or decision until there is agreement. Anyway, so those are just a handful of ways around high quality data. Appen.com, we specialize in this, so happy to go through that more detail.
Yeah, I largely agree with that. I mean, data is sort of the single most important aspect when you want to train high quality computer vision algorithms. So, it's often a gut check to see how well your computer vision model will perform if you actually go through the annotation process yourself. If you're able to do, a good job at annotating data yourself, it's likely that you will end up with a model that can also, well, up to certain limits, but that can also, do well. But if you're having trouble with, covering all the corner cases or actually, following the same instructions that you drafted to annotate data, then it's often a sign that, hey, look, you're not going to get good data and it's probably going to not reflect well in your model. And the other things, I mean, apart from getting high quality data early on, there's a lot of training strategies that we all have explored over the years. Things like data augmentation, things like fine tuning over existing models. These things really help you overcome the challenge of not having enough data. Right? Data is not cheap; it's expensive. But these techniques that have come across over the last few years of just doing more with existing data is often quite beneficial in most practical settings, and it often gives you that little bit of delta to give a boost to your trained models.
I can add that, given that we work in synthetic data, I think there's some really interesting things we've discovered with computer vision and synthetic data. So one thing in terms of the question itself around what techniques are very popular, for us, we use a ton of transfer learning. And so what we do is we actually think of synthetic data, so data simulated from like a photorealistic 3D world. At a high level, synthetic data really actually can be very powerful in terms of acting as a prior for a neural network. There's no such thing, if you think about Bayesian frameworks around machine learning, priors are a way that, like a prior belief about the world. There isn't a really coherent way of creating that in the neural network. And synthetic data can actually acts as a way of creating a prior belief around that world. And then the transfer learning then acts as a way to fine tune that prior belief in real world data to also match things like sensor adaptation and stuff like that. And so, our core belief, one of the things is that we actually think that synthetic data is going to be a very powerful complementary paradigm shift to the way people typically train computer vision algorithms. And basically what we found is that just using a little bit of real data and a lot of synthetic data can get really good performance actually. So, yeah.
That's really interesting. And actually, so we've had a couple questions come up in chat around training approaches for autonomous driving. And so I think I'm gonna punt those to Vladimir, as I have not worked at all on autonomous driving.
So again, I cannot get into details, but main idea is the same. Of course, it is transfer learning everywhere where you can. It's like one thing. Of course, it's like data augmentation. It can be simple data augmentation, like spatial transformations, like rotations, flips, etc. Or it can be something like crazy when you play with colors and do like weird distortions and this type of the thing, which is kind of like similar to any other computer vision or any other type of deep learning task. I would like to add that the difference between autonomous driving and maybe some other areas that, let's say you work on some other task and you reach some accuracy of 80%, and then you're looking for some product applications. Maybe you can use this prediction of your model as a ranking. It's not perfect, but still you may find some value. For autonomous driving, story is slightly different. You cannot say, okay, like my algorithm is 80%, like accurate is good enough. Let's go to the road and do some kind of like killing machine. You want something that's extremely accurate, and of course you cannot reach this. I mean, it's machine learning, and people don't use like 100% accuracy in machine learning in one sentence. And to balance this inaccuracies, like in autonomous, we use a bunch of different sensors, and let's say people detect pedestrians based on like LiDAR and camera and moving objects using radar, and then some kind of like early sensor fusion and late sensor fusion and like double checks everywhere. So in this sense, autonomous may be different from other applications that I've seen of machine learning due to the fact that you need something like perfect or close to perfect.
That makes the problem so much harder.
And it's interesting.
Yeah.
I mean, in some applications, you know, to Vladimir, you were talking about medical imagery earlier. There are times, you know, when our accuracy in one aspect, for example, we're okay with false positives, but we're really not okay with false negatives, say in cancer detection, you know? So it's far worse to incorrectly say someone is cancer free than it is to say, I'm sorry, you have cancer, and they later find out, phew, they don't. And so I think also kind of in the medical setting, wherever people's lives are greatly impacted, that need for accuracy in as many ways as possible becomes a critical issue.
I think the other thing when it comes to self-driving is like data completeness, right? And integrity. So, you know, just this week, there was another example where Tesla on autopilot hit a semi-truck. And this also happened a couple of years ago, right? And there was a truck perpendicular in the road, and the car slammed straight into it. Now, that's a good example where there probably weren't a lot of training examples where there's a truck perpendicular in the middle of a freeway, right? Because that doesn't happen very often. You know, obviously this is a level 2, you know, autonomous system. It's not a level 4 or 5, right? And so there's a lot of reasons that could have happened, and you know, areas for mistake and that to go wrong. But one place is around, you know, completeness of your setting. So, you know, it doesn't shock me that there's probably low volumes of data in, you know, nighttime driving or rainy condition weather, or, you know, things like that. And this is, I think, you know, to where real data can complement synthetic data, right? And there's opportunities for synthetic data to create a lot of data in the places where capturing real data is not possible, right? Because there's not a lot of examples. The challenge with synthetic data is that you can only create the data that you can think about and imagine ahead of time, right? And so you're limited by all the use cases that you can think of, where in reality and real data collection, you're not limited by what you can think of, you're limited by what you can capture. And so, you know, those two approaches in complementary uses, I think, can provide really high quality outcomes.
Yeah, that's absolutely right. Sorry, Abhishek. Yeah.
There are two aspects here, right? There's a data collection aspect and there's a data annotation aspect. And to address the issue of coverage, you know, to make sure that you've covered all, you know, a fair distribution of your data, it's often useful to at least, you know, have a model in the loop itself in the data collection stage, right? So if you're looking for, let's say, you know, if you're looking for training data for doing, let's say, face detection, you know, it is often beneficial to have a model in the loop which can actively tell you to, hey, you know, sample more people from Asia if you don't have that in your data set already. So those things can easily be done with a supplemental model in the loop, which can sort of actively select the data that you will then send for annotation. So that, again, you know, bridges some of this gap of not having or having sparse data in certain parts of your data distribution.
Yeah.
I think also, you know, particularly with autonomous driving, it presents a very unique problem, which is that those extreme scenarios, you know, the semi-truck across the road, those are going to be often the most dangerous. And so the things that are truly catastrophic, thankfully, don't happen with a high degree of frequency, but those are the things that we really need to plan for. And that's kind of a classic emergency management problem, is that the rarest things are the most catastrophic. So we have to not prepare for the common every day, but we really have to prepare for those rare things, because that's going to be what will truly have the greatest impact.
And that's actually reflected in our business as well. I mean, it is very much like, okay, we don't want to just simulate, you know, the stuff that you see every day. We want to simulate all the stuff you can't see and all the things that we really have to be concerned about. But just to Alyssa's point, I think there's, you know, there is a beautiful marriage between synthetic and real world data. And I think the two are absolutely necessary to push computer vision forward. So
it'll be interesting to see where that goes in the future, for sure.
Mm-hmm.
All right, so, and then I believe, let's see, this is our second to last question. What does your computer vision toolkit look like? Be specific. And I imagine with so many different backgrounds, we'll have some very different answers here. So who would like to start talking about their computer vision toolkit?
I can talk about just our whole sort of, we have this thing what we call like this virtuous cycle of improvement in our company. And it starts with the sort of synthetic data generation. And then we benchmark that on a real world data set, right? To just sort of see how that looks like. And then we do a bunch of benchmarks, but one of that is just the synthetic alone. And another thing is we engage in domain adaptation. It's a sort of area of computer vision that tries to use things like generative adversarial networks to try to improve the synthetic data itself using real world labeled images. And then we benchmark that, and then our toolkit is essentially getting those benchmarks, figuring out where we need to actually improve, improving the simulator from there, and then keep iterating over and over again. So for us, it's a process in terms of the actual tools, like PyTorch. We were big users of PyTorch. We definitely use things like polyaxon to orchestrate a lot of our experiments, things like that. So I don't know if that's helpful, but that's just sort of how we work at our startup.
No, that's a great place to start. Who wants to also share their toolkit?
Okay. Abhishek, go ahead.
Go ahead, Vladimir.
Okay, so first of all, in terms of computers, I don't use MacBooks. I consider the operation system unacceptably ugly. So it's like, I use Linux. So for my, my main programming language is Python. I use PyTorch and I use Keras plus TensorFlow. Really depends on the task. PyTorch like became mature in the last 2 years like a lot, but still it has like a lot of limitations. Let's say if you're talking about like mobile, TensorFlow Lite is much better. For data augmentations, I use library Albumentations, and I use it because it's like pretty fast, and also because I'm one of the developers. For traditional computer vision, I use OpenCV and sometimes Scikit-Image and other libraries. Probably that's it. So yeah, PyTorch is my main deep learning framework.
That's been my experience as well. Abhishek, you were going to say?
Yeah, I mean, apart from these sort of more tools and frameworks, it's also, I think, becoming quite increasingly common that a lot of the detectors or slightly things like detection or maybe even segmentation or classification, these modules or these algorithms have become increasingly more accurate to the extent that these can also be readily used as sort of an off-the-shelf black box, if you will, right? So it's often useful to have a lot of these handy or be familiar with how to use some of these off-the-shelf techniques to be able to do, things on top of it, right? To be able to maybe filter out your data or make more high-level inferences based on these smaller building blocks that have become more and more increasingly accurate to the extent that they can be modularized and used in a black box manner.
I think there's both technical tools and business process tools that can be put in place for successful teams to launch, a computer vision based product for the production, right? So part of it is some of the technical infrastructure around data processing and model building and testing and monitoring and data collection and annotation and all that. Also, there's sort of business process tools that you want to put in place to kind of complement and parallel those technical tools along the way. So things like, ethical or responsible AI deployment guidelines, right? Or things like stakeholder buy-in or, controlling for model drift or data drift, right? And to be able to sort of accept change over time or to have processes in place to update the model over time, according to changing business needs.
That makes a lot of sense. And I think the two have to just by definition go hand in hand. So, all right. And then our final question is, and this will be a really fun one, so I'm interested to hear what people say. What is the future of computer vision within an enterprise setting? And so I think I'll save my opinion for last, because for me, it's a very specific application in kind of disaster scenarios, but I would love to hear kind of for more businesses and commercial applications, how everyone here thinks, what is the future of computer vision?
Well, I think the whole deep learning revolution in some sense for over the last 5-7 years have really brought a lot of things, have reduced the bar to try out a lot of things to help you in your own problems, right? So it's become more and more easier for many more people to try out things like, face detection or image labeling or classification or segmentation and things like that than it was before. So the bar to entry has been lowered, and I think that will enable a lot of people to try out different techniques in their own settings. They may not be using the most optimal algorithms or optimal models for their own problems, but at least it'll allow them to get their hands dirty. It'll allow businesses and people who are not in the computer vision field to be able to try out these things quickly and see if there's a benefit. And if there's a benefit, then you can double down, maybe collect more data, solve the problem specific to your needs, but at least it'll allow more exploration to happen because you can now try out these algorithms which have matured to a great extent in a relatively short period of time. So I think you'll see an acceleration of an adoption of these kinds of techniques across a whole range of industries.
Alyssa, you were saying?
Yeah, just completely agree with what he just said. I think experimentation and diversification of applications and use cases we'll see as the barriers to entry are lower. So yes, agree.
This time around now, with computer vision, reminds me actually of like 6 years ago. I used to work at the New York Times. I was one of their first machine learning people that was brought in there. And back 6 years ago, this concept of being a data scientist, it started like getting on fire. Like everybody was like, oh, everybody needs a data scientist. We need a data scientist. Every company started getting on this ramp of hiring data scientists to analyze data. And now, like almost every company has like, any serious company has a data scientist. I sort of feel like computer vision now in the next 2 years is going through that phase. And I think part of what spurred it about 6-7 years ago in terms of this rise of every company having a data scientist was, one, the tools were really great. The tools, just like data science tools like Pandas, things like that, scikit-learn, all those tools were being built. It was really easy to use. And so you had this like much easier adoption to a lot of what people are saying. The other challenge, I think, is data as well. A lot of companies already have data that was already built in. So I think what's interesting to sort of figure out with computer vision is how easy will it be to get what I think is the most important resource, or the most difficult resource to obtain, which is really good data. And so solving part of that problem, I think, is going to be important to help spur it so that it's not just a 1 to 2% market penetration, but it's more like a 20 to 30% market penetration in terms of computer vision technologies.
I would completely agree. I think, there's that kind of saying, I guess, that the models are only as good as the data, really. And so one of the challenges that I've really seen in some of the organizations that I work with adopting computer vision more broadly is that data problem, is having good data, is having a lot of it, and having reliable or verifiable data. And in particular, I think, the other obstacle to having kind of true enterprise-wide adoption in terms of emergency management and emergency response is that the kind of black box approach isn't always going to work, because there needs to be a high degree of explainability if we're going to be using this to make massive life or death decisions. Sure. And so the kind of off-the-shelf applications often really actually turn people away, because if you're unable to really explain in simple terms how something works, then your everyday person who needs to use it or wants to get data or results from it isn't going to trust it. And that trust is really, really key for decision making. And so I think if we can kind of tackle those, and it's not a technical problem, right? It's an education problem. It's a documentation problem. And I think if we're able to kind of focus on that and really grow that, then we'll see larger adoption of computer vision.
Yeah, absolutely.
I have a question to Jesse. So yeah, I totally agree with like other speakers. Definitely, computer vision is maturing. Definitely, that is important, and everything is like growing pretty fast. But you mentioned applications of computer vision in physics. What do you think are perspectives of deep learning and computer vision techniques in different branches of physics?
So I think
How
I
will
think
it grow?
Yeah, well, so I think that's going to be, it depends on the branch of physics, right? And this is kind of like the hilarious thing about physics is that it runs the gamut of your almost like Luddite, I do everything on pen and paper, I refuse to use a computer approaches, and then all the way to the most high tech at the forefront applications. And so obviously I think the branches of physics that are more at that forefront are going to adopt things like computer vision a lot quicker. I would say I think the more visually based physics applications, so I'm biased, but I think astronomy is really one of those areas where computer vision could really take off, mostly because of just the high volume of data and the low volume of astronomers, that we really do need the help classifying images and identifying objects in imagery, especially with critical missions like near Earth asteroid identification, as well as satellite trajectories. So I think there are a lot of amazing applications specifically for astronomy that I would love to see, but I think it's going to be, these are very highly academic disciplines, and so often, unfortunately, academia can trail behind commercial enterprises sometimes. And so I'd be interested to see. I think it has a great impact. I'm not sure about whether or not it'll be entirely accepted. So, but yes.
Amazing. You crushed it. All of you were super awesome. Looks like everyone's stuck around. And so we are a couple minutes past the hour, but if the 5 of you are okay, I'd like to take a couple more of your minutes to at least hit a couple audience questions, which we've done some of throughout, but let's see quickly. So there's a couple questions, like one about, pushing computer vision models more to the edge and how will the chip stuff progress there. And there's another question around like computer vision with robotics in micro cities. And so generally like hardware, computer vision, what are your thoughts? Is it just more GPUs, some idea of a better GPU, or do you have other more progressed thoughts on the hardware?
I think edge computing is fascinating. I think it's powerful. I think there's going to be a lot of really good things happening there. I'm seeing a lot of good research on sort of neural network pruning, being able to sort of compress the architectures to allow for more efficient inference. So I think there's a lot of exciting work there. But for a lot of the things in which computer vision will be an active part of our lives, a lot of it's on the edge. It's going to be on our phones. It's going to be in our CCTVs. It's going to be in all sorts of cars, autonomous vehicles. So being able to sort of empower an edge device with computer vision is, I think, going to be a huge part of the future. And especially with things like 5G networks, where you're going to be able to actually transmit. You don't have to actually run it and maybe be able to just do that on the cloud. That opens up a lot of opportunities as well. So I see a bright future there for sure.
I think this goes back to what is the goal of the model and what the decision is that you're making and where is it appropriate to make that decision, right? So, you brought up Blue River Technologies at the beginning of this panel, and what they're trying to do on the edge is make a decision around whether or not to put pesticides on a particular plant and determining whether or not that plant is a crop that the farmer is trying to grow or is a weed that they're trying to not. That's a fairly simple computer vision sort of classification problem, right? It either is or it isn't. There are, differences like, Apple's doing work around, unlocking your phone, right? Based on facial recognition technology. That's a more complex decision, computer vision problem, because you're trying to identify, is this person that's in front of the camera right now, the same person that, this model was trained on to, unlock this phone. So I think, it depends on the sophistication and the complexity of the model and the decision that you're trying to make, and how urgent is it that you make it at the edge, right? Or, is there appropriateness in that business case, to allow for the time that it would take to, call back to a server, and process that, sort of introduce that latency. And then, also it's inextricably linked from the camera, right, that you are, as the sort of visual input, to this model, right? So I think, all of this stuff is linked together, but it goes back to the complexity of the decision, the urgency of the decision, and, how that is how urgent it's needed to be on the edge.
And there's also the issue of privacy, right? If I don't want my data to leave my devices or my home, edge computing is the only way to do any computer vision. So that's become more and more important over the last couple of years. So as we see, more awareness around privacy, I think edge compute is just going to be more and more important around us.
Definitely, and I would agree as well for kind of like the disaster environments, because it's a privilege to be able to throw a bunch of hardware at the problem and to be able to say, oh, just add a lot more hardware and we'll be fine. But especially in disaster scenarios where you may not even be able to have network devices, everything has to be done kind of in individual pieces of hardware. And not only that, but they have to be fairly resilient and be able to withstand a lot of, the elements and various kind of effects that can happen at a disaster scene. And so I think it's going to be interesting to see not only how computer vision at the edge progresses, but in that kind of resilient way that allows for a lot of different applications.
Awesome. All right. So there was my hardware inquiry. And then I have one other question, my last one, which covers like...
I apologize. I had to drop off. Thank you so much for everyone's time.
See you, Alyssa.
See you, Alyssa.
And then I have one other that covers like three people's questions, which is around facial recognition, using CCTV, data, GDPR, which could obviously be a whole other panel. But what are your thoughts on just the whole computer vision, facial recognition, I guess, debate, use case, etc.?
Oh, sure. I'm happy to tackle it, and then hopefully, so this is a much larger conversation, of course, right, on the ethics of how some of this stuff should be used, and a lot of people talk about sort of the neutrality of technology and use that to brush away the ethical concerns around how this should be used. I think there is truth around the neutrality of technology. There is, but I actually think it's more important to think about it as a reflection of who we are as a society. So if we're a society that believes in dictatorships, if we're a society that believes in control of its citizens, then of course that technology will be used as a way to recognize and control citizens. But I think it's an important conversation that we have to be actively having around how this technology is being used, what are the limitations we can put into it, and be able to be open about that. And I think technology leaders and everybody, practitioners in this space, should educate themselves about what it is regarding our civil liberties and what we want to actually create and how we want to use this technology. I know it's a really big topic, so happy to dig more into it, but that's my perspective at a high level.
Yeah,
I would agree. And I think, I think that whatever, you mentioned a lot of approaches and considerations and things that we need to think about. And I would say that, like, the optimist in me completely agrees with you and thinks that these are considerations that we always need to have when developing models. But kind of a little bit more of the pessimist in me says that unless it's backed up by policy and potentially law, then just having the considerations will never be enough. And so I think this is kind of where the AI ethics and AI law definitely overlap, where this is going to be an area where we're going to need codified policies and laws in place to protect people, because there's always going to be, I think, someone that takes it too far.
For the record, Jesse, I totally agree with you that policy and law has to get involved there. And it's not just about just the good conscience of somebody creating a technology and thinking that it will always be used for the right reasons. So I definitely think that has to be in place. Yeah.
I would like to add here, so often in these discussions, I totally agree that it should be like, we need to think about this, and it should be like, proper policies that different like parties should like agree and think carefully through. So often people have this question, okay, should we ban facial recognition technology or not? And I don't think this answer is correct. As we discussed before, off-the-shelf solution for facial recognition and comparing different like embeddings from facings, they work so well and they're so lightweight. So technically you can get something GitHub, you clone the repo, you take some pre-trained weights, and some kind of like face tracking and face recognition technology is already in your hands. And smart high school kid can already do and implement this, combine different pieces together and like use some publicly available CCTV cameras for like scanning and analyzing this piece. So in this sense, there is no way that we'll be able to ban this technology. We'll be able to ban this, I don't know, like to prohibit companies from using it. This is possible, but like complete banning is just not possible. This technology is already with us.
Agreed.
I would say that it's, for me, at least in my mind, Vladimir, it's more about the consequences of how you use this technology. So if we have the right policies in place that say that if you use this for just detecting, just whatever, your dog in your own house, it's not the same consequence as you using it to get personal identification on people so you can steal money from their accounts and things like that. I think about it more around what are the consequences of using this in a certain way, rather than banning it.
My point is more about like, how can you enforce not using or using this technology?
I think you can do it based on use, like different use cases. So I completely agree. I don't think you're ever going to be able to ban a technology outright, but I think it's going to be, perhaps, this kind of gets into a lot of conversations about autonomous weapons, right? So potentially you could say, you could ban the use of computer vision for automatic targeting. You could ban the use of computer vision for identifying, for maybe using CCTV footage as training data. You could set specific parameters around that, or specific organizations that can and cannot use it. And I would say that to me would be more effective than trying to pursue a blanket ban. But it has to be based on use, because to Daeil's point, I think technology in a lot of ways can be neutral, but it's the data that it's fed in the case of machine learning, and then it's how it's used that makes it not neutral. And so to that point, there has to be legislation, or there has to be policy around the data used, and then again around how the technology is applied.
Yeah, I think the former issue that you mentioned, Jesse, about the bias and the fairness in the model itself, I think we, as technologists, there are ways that we know of to at least mitigate that issue to some extent. But the other issue of how it's, where all it's going to be used and whether it's misused or not, or whether it should be used at all or not, that I think is a bigger question that I think Daeil also mentioned, that it needs a more societal approach, whether we want to be one way or the other. Yeah.
All right. And with that, I am going to call it. That was a very nice end to a big topic. So thank you so much to all of you. Jesse for moderating, great work. Daeil, Abhishek, and Vladimir for panelists, and Alyssa, thank you. Hope your meeting is going well. And we'll send a recording around to everybody shortly. And yeah, thank you so much to the four of you and Alyssa for spending some time with us.
Yeah, and thanks Michael and Jesse as well.
Invisible claps.
Great.
Thank you.
Thanks. Okay.
Thanks.
All right. Be
Bye.
safe.